just like with isomorphisms, homomorphisms also have a number of properties that come just from the fact that they preserve structure. The first thing to notice about homomorphisms is that this property of preserving structure, which we define like this, it is equivalent, just like with isomorphisms, the property of preserving structure is equivalent to preserving linear combinations of two vectors, and that's also equivalent to preserving finite linear combinations of vectors, right? All three of these things are equivalent for exactly the same reasons as when we were working with isomorphisms, right? The proofs that we wrote down for these didn't actually depend on the fact that we had an isomorphism. Something similar goes for the fact that a homomorphism sends the zero vector in its domain space to the zero vector in its range space. Although the proof that I wrote down for isomorphisms actually subtly did use the fact that we had an isomorphism, but this is still true for homomorphisms. So to figure out what happens to the zero vector in V, just notice that the zero vector in V is the same thing as zero scalar product with the zero vector in V, but right, if this is a homomorphism, we can move this scalar outside of the map. So now we have zero scalar product with f of the zero in V, but now it doesn't matter what f of the zero in V is. Zero times that is going to be the zero in W, right? So now we see that the f of the zero vector in V has to be the zero vector in W. Okay, a similar thing goes for additive inverses, right? You can just write this additive inverse as a scalar product with -1, and then move the -1 outside of the homomorphism, and then you're done. Another interesting fact about isomorphisms was that they were totally determined by what they do on a basis, but actually the same is true for homomorphisms. So if you go back and look at the proof of this fact for isomorphisms, we never actually used the fact that the function was one-to-one or onto, I don't think. So the exact same proof works just as well for homomorphisms, or linear maps, as it does for isomorphisms. So if two homomorphisms, if two linear maps agree on a basis, then they actually are exactly the same function. This is going to be kind of a key fact that lets us characterize and understand all of the homomorphisms that exist between two spaces, because it gives us some nice way of describing a homomorphism without having to write down the value that it takes on every single vector in the whole space. You only have to write down what it does to a basis for that space, which is going to give us a sort of a shortcut for understanding what a homomorphism is doing. All right, so homomorphisms have these nice properties, but one thing that we'll often want to do is produce a homomorphism with certain properties. And there is a nice procedure for doing that. So suppose that we want to define a linear map from V to W, from some vector space V to some vector space W. And suppose we have let's deal with finite dimensional vector spaces here. Suppose that we have a basis for V, so beta 1 through beta n. How much information do we actually need? Well, if we're going to define a function from V to W, definitely we have to say what the value of this function will be on beta 1 and beta 2 all the way up to beta n. So let's give ourselves, let's suppose we know what we want f of beta 1 to be. Suppose that we know we want that to be W1. And suppose we want f of beta 2 to be W2, and so on. Right? All the way up to beta n is Wn. Now, by writing this down, I'm not implying that the w's should form a basis for capital W. W1 through Wn might be linearly independent, they might be linearly dependent, they might not span all of W, they really could be any vectors in capital W. So what I'm just saying, suppose we know what we want to have happen to the basis vectors, right? So what we have now is a function from this basis, so let's call this basis capital B. We have a function from this basis to W, right? And these vectors could be anything. Of course, different choices for these W1 through Wn will give you different homomorphisms in the end, but any choice of W's will give us a homomorphism in the end. All right, so we have this function from the basis vectors to W. This is enough to totally determine what the homomorphism does. As we kind of saw with isomorphisms, this should come as no surprise because we know that if two homomorphisms agree on a basis, then they're the same homomorphism. So it kind of stands to reason that knowing what, or having a function only on a basis should give you a homomorphism. But let's check why that is. So the idea here is that since we know what happens to a basis, and since every vector in V we can write uniquely as a linear combination of the basis vectors, insisting that our function preserve structure will tell us what the result is for any vector. So the idea here is we can extend f to, I'll call it f hat. So we're extending it so that its domain, instead of just the basis, will be all of V as follows. All right, so to define f hat of V, right, we have to know what f hat does to any vector in V. First, write V as a linear combination of the basis vectors. So a1 beta 1 plus dot 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 up to a n beta n. And there's a unique way to do this. Right. And this is important because, of course, we're going to use these coefficients to define f hat. If there were more than one way to write V as a linear combination of the betas, there would be no consistent way to define which coefficients you use to define f hat. But since we have a basis, these coefficients that express V as a linear combination of the betas, these coefficients are unique. All right, so now we can let f hat of V be a1 f of beta 1 plus dot 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 up to a n f of beta n. All right. Of course, we need to show that this this map does preserve structure, right? I guess before we do that, let me point out that we had no choice in this definition, right? If we want these basis vectors to get sent to these outputs, and if we want our function to preserve structure, then there's no choice for what should happen to this vector. If f is going to preserve structure, it has to send this vector to that, right? So really, there was no choice in this definition. The only question is, does the result still preserve structure? So to check that, let's see what f does to a linear combination of two vectors. To write our vectors, I'm going to write them as linear combinations of basis vectors because this is linear algebra and that's what you do. So we'll have our first scalar will be x1 and our first vector will be a1 v1 plus, a1 beta 1. That's a beta. a1 beta 1 plus dot 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 up to a n beta n. Okay, plus, now we're doing a linear combination of two vectors, so we need another scalar and another vector, and our vector is b1 beta 1 plus dot 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 plus bn beta n. Okay, So what does f do to this? Well, to know what f does to this, we have to write this big vector inside here as a linear combination of the betas, right? Because then we just use the coefficients in this way. So in other words, we have to combine like terms according to what betas show up. So this is f of x1a1 plus x2a2, sorry, x2b1, sorry, times beta 1 plus dot 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 up to x1an plus x2bn, yes, this should be b1, beta n. Okay, and now that we know what the coefficients on the basis vectors are, now we can write down what the result of f is, right? We just move the f to the betas, essentially. So this is x1a1 plus x2b1 times f of beta 1 plus dot 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 down to x1an plus x2bn times f of beta n. And sure enough, right, if you multiply all these out and regroup according to where the x's are, we have x1 times a1 f of beta 1 plus dot 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 plus an f of beta n, okay, plus x2 b times b1 f of b beta 1 plus dot 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 plus bn f of beta n. Okay, and this is equal to x1 f of a1 beta 1 plus dot 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 up to a n beta n plus x2 times f of b1 beta 1 plus dot 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 plus, I'm out of room, bn beta n. Okay, so right, we took f of a linear combination and we got the same linear combination of f applied to the individual vectors that we started with. So this shows that this definition, which I remind you we had no choice about, we were forced to use this definition to come up with a homomorphism that takes these values on the basis vectors. This definition does produce a homomorphism. So knowing what homomorphism does on a basis forces the rest of the values of the homomorphism on us. All right, let's look at an example of that. Yeah, so this just summarizes what we just proved. Right? Given a function, you have a unique way. There's only one way of extending a function on a basis to a function on the entire vector space. All right, let's look at an example. So here is a function on, so for P3, this should be a subscript, not a superscript. For P3, we have a nice basis. Right? There are many, of course, many bases for P3, but one nice one that we've used in the past is 1x, x squared, x cubed. Right? So we can define a homomorphism on all of P3 just by saying what each of these vectors does. I didn't say what our range space should be. So we're defining a homomorphism that for now I'll call F. This is from P3 to, we could regard it as a homomorphism to P3 or to P2. But I guess for now let's say P2. Okay, so to define this on all of P3, we only have to say what it does to a basis of P3. And here I am saying what it does to a basis. It sends the polynomial 1 to the polynomial 0, the polynomial x to the polynomial 1, the polynomial x squared to 2x, and the polynomial x cubed to 3x squared. All right, and this extends in a unique way to a linear map on all of P3. So what is this linear map? What is this homomorphism? Well, if we just write down, if we figure out what this linear map does to any polynomials, any polynomial of degree less than or equal to 3, so right, that's going to be a plus bx plus cx squared plus dx cubed. Remember that the way that you extend a function on a basis to a linear map on the whole vector space is just by sort of forcing the preservation of structure. And if we force the preservation of structure, then f applied to this whole polynomial gives us, so we can move this a outside, a times f of 1 plus b times f of x plus c times f of x squared plus d times f of x cubed, right? Extending by preservation of structure is how you extend from a basis to a homomorphism on the whole space. Okay, so this is, right, f of 1 we said was 0, so this part's 0. F of the polynomial x we said is the polynomial 1, so this is b times 1. And then c times f applied to x squared is 2x. And then finally f applied to the basis vector x cubed, or the basis polynomial x cubed, is 3x squared, so d times 3x squared. Okay, so what do we get? Altogether we have b plus 2cx plus 3dx squared. All right, so why did I look at this example? Well, look, what linear transformation turns, or what linear map turns this polynomial into that polynomial? Do you recognize this? It's just the derivative, right? So the derivative does exactly the same thing on the basis vectors 1x, x squared, and x cubed. So this thing I've been calling f the whole time is actually just the derivative operator. Right? So the derivative operator is a homomorphism. It's a linear map from P3 to P2. P2. In fact, it's more than that. It's an operator from the space of all polynomials to the space of all polynomials. Right? So this is sort of a big example of a homomorphism on an infinite dimensional vector space that we're familiar with, even though we don't usually think of it as a vector space homomorphism. It is, and in fact it's from one infinite dimensional vector space to another. So it's sort of a weird example in that way.